Everything you see in the night sky is a lie. Not a malicious lie, not a deliberate deception, but a lie your brain tells you the moment you look up and see thousands of stars scattered across the darkness. It feels full, it feels infinite, it feels crowded with light, but it isn't. Tonight, we are going to dismantle that illusion piece by piece. And by the time we're done, you'll understand something deeply unsettling. The universe is not just big. It is almost completely empty. Go somewhere far from city lights. Let your eyes adjust. Wait for the sky to darken into velvet. And then look up. The Milky Way stretches across the sky like a river of shattered diamonds. Thousands of stars are visible. If you've never seen it clearly, it can feel overwhelming, like the universe is overflowing. Your brain interprets density based on brightness. Yeah, points of light against blackness trigger a primitive assumption. There must be a lot out there. But here's the first crack in the illusion. Every single star you can see with your naked eye, every one, exists inside your immediate cosmic neighborhood. The farthest visible stars are roughly 15,000 light-years away. That sounds enormous. And on human scales, it is. But the Milky Way itself is about 100,000 light-years across. That means when you look at the sky, yet you are seeing less than 15% of your own galaxy, not the universe, not even the whole galaxy, just a tiny local bubble. It's like standing in your backyard and assuming the entire planet looks like your lawn. Now let's widen the lens. In 1995, scientists pointed the Hubble Space Telescope at a patch of sky that looked completely empty. No visible stars, no glow, just darkness. The patch was so small that you could cover it with a grain of sand held at arm's length. And then they waited. For 10 days straight, Hubble collected every photon that entered its mirror from that tiny black patch. What they found changed astronomy forever. Inside that seemingly empty speck of darkness were roughly 3,000 galaxies, not stars, galaxies, each one containing hundreds of billions of stars. Let that sink in. A patch of sky the size of a grain of sand held at arm's length contains thousands of entire galaxies. Yet this image became known as the Hubble Deep Field. 4. When astronomers repeated the experiment in different directions, they found the same result. Everywhere you look, even in the darkest void, there are galaxies. Billions of them. Trillions, according to updated estimates. At first glance, this seems to destroy the idea of emptiness. If there are trillions of galaxies, each with hundreds of billions of stars, then the universe must be unimaginably full, right? Yet here's where the illusion collapses. Let's do something dangerous. Let's do the math. The observable universe is about 93 billion light-years in diameter. Inside that enormous sphere are roughly 2 trillion galaxies. 2 trillion sounds absurdly large. Each galaxy contains, on average, about 100 billion stars. Multiply those together and you get approximately 200 billion trillion stars. That's a 2, followed by 23 zeros. It feels incomprehensibly massive. But numbers are deceptive without scale. So let's compare volume. A star like our Sun has a diameter of about 864,000 miles. That seems large. But the observable universe has a radius of about 46.5 billion light-years. Convert that to miles, and you get a number so large it barely fits in human thought. Now calculate the volume occupied by all stars combined. Then compare it to the total volume of the observable universe. The result? And stars occupy less than 10 to the negative 49th power of the universe's volume. That's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000
To put that differently, if you shrank the entire observable universe down to the size of Earth, all the stars combined would occupy less space than a single proton. Not a mountain, not a grain of sand, a proton. And that's just stars. Most of a star is empty space between atoms.
Yes, and most of an atom is empty space between its nucleus and electrons. The matter you think of as solid is already mostly nothing. So when we say the universe is empty, we're not exaggerating. We're being precise. Now zoom back into our own galaxy. The Milky Way contains roughly 200 billion stars. It spans about 100,000 light years. The nearest star to our sun is Proxima Centauri, about 4.2 light years away. That if you shrank the sun to the size of a grain of sand, the nearest star would be about 20 miles away. 2 grains of sand, separated by 20 miles of emptiness. That's the average spacing. And galaxies? Our nearest large neighbor is the Andromeda Galaxy. It sits about 2.5 million light years away. The Milky Way is only 100,000 light years wide. That means the distance to Andromeda is 25 times the width of our entire galaxy. Yet imagine 2 cities separated not by miles, not by continents, but by 25 entire galaxies stacked end to end. Between them? Mostly nothing. Vacuum. Darkness. A few stray dwarf galaxies. That's it. And here's the part that makes it worse. Everything we've counted so far, stars, gas, dust, galaxies, makes up only about 5% of the universe, 5%. The remaining 95% is something else, something invisible, something we cannot see, touch, or directly detect. When astronomers measure how galaxies rotate, they find that visible matter isn't enough to hold them together. Stars in the outer regions move too fast. They should fly apart, but they don't. Something unseen is adding gravitational pull. We call it dark matter. And it outweighs normal matter by roughly 6 to 1, meaning even the tiny fraction of the universe that isn't empty is mostly made of something invisible. But dark matter doesn't make space feel full. It doesn't emit light. It doesn't glow. It doesn't interact with you in any meaningful way. Right now, as you're listening to this, dark matter particles are passing through your body. Billions of them every second. You don't feel them. You never will. Because they barely interact with normal matter at all. They just pass through, like you aren't even there. And so even where the universe isn't empty, it might as well be. Now imagine scaling everything down. Shrink the observable universe to the size of Earth. All stars become smaller than a proton. All galaxies become subatomic specks. And the rest? A vast, featureless void. That's the real picture. The night sky feels full because your brain compresses scale. because black space between bright points doesn't register emotionally. But physically? The universe is an ocean of nothingness. Thin filaments of matter stretch across unimaginable distances. Tiny islands of density scattered through infinite dark, and those islands are drifting farther apart because the space between them is growing, faster, every second, which leads us to the next layer of the lie. The universe isn't just empty. It is becoming more empty, and something is actively pulling everything apart. Something we didn't even know existed until 1998. In the next chapter, we'll explore the invisible scaffold that allows galaxies to exist at all, and the even darker force that is slowly tearing them away from each other. The sky isn't just lying to you. Reality is stranger than you think. If the universe is almost completely empty, then galaxies shouldn't exist. That's not dramatic exaggeration, that's physics, because gravity is weak, unimaginably weak. If you hold a paperclip in your hand, the entire mass of the Earth is pulling on it with gravity, and yet a tiny fridge magnet can overpower the entire planet's gravitational pull. That's how weak gravity is. So how did gravity manage to gather gas across millions of light years, compress it into stars, assemble those stars into rotating galaxies, and hold those galaxies together for billions of years? By all visible accounts, it shouldn't have. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a massive cluster of galaxies called the Coma Cluster. The cluster contains thousands of galaxies bound together by gravity. Zwicky measured how fast those galaxies were moving, and he noticed something deeply unsettling. They were moving too fast. Based on the visible mass, the stars and gas he could see, the cluster didn't have enough gravity to hold itself together. At those speeds, the galaxies should have escaped. The cluster should have flown apart billions of years ago, but it hadn't. Zwicky did the calculations again and again, each time the same conclusion. There had to be far more mass present than what was visible. He estimated the cluster required roughly 400 times more mass than what he could account for. He proposed a radical explanation. There must be invisible matter, matter that has mass, matter that exerts gravity, but matter that does not emit light. He called it dunkle materie, dark matter. Almost no one believed him. It sounded absurd. Invisible mass? Matter that doesn't interact with light? It felt like patching a broken theory with a ghost. So for decades, the idea was largely ignored, until the 1970s. An astronomer named Vera Rubin began studying how stars move inside spiral galaxies, including galaxies similar to our own Milky Way. She expected something simple. In our solar system, planets closer to the Sun orbit faster. Mercury moves faster than Earth, Earth faster than Mars. Because gravity weakens with distance, galaxies should behave the same way. Stars near the center should orbit quickly. Stars far from the center should orbit more slowly. But that's not what she found. Instead of declining with distance, the rotation curves flattened. Stars in the outer regions were orbiting just as fast as those near the center, sometimes even faster. That's impossible, unless there is additional mass in the outer regions. Mass that isn't glowing, mass that isn't visible, mass that extends far beyond the bright disk of the galaxy, dark matter. By the late 20th century, the evidence became overwhelming. Dark matter wasn't just in galaxy clusters, it wasn't just in a few anomalies, it was everywhere. Galaxies are embedded inside enormous spherical halos of invisible mass. You have the visible galaxy, the spiral arms, the glowing stars, the dust lanes, is only the bright core. The real structure is much larger. The Milky Way has a visible disk about 100,000 light-years across, but its dark matter halo may extend 600,000 light-years or more, 6 times wider than what we can see, and that halo contains roughly 85% of the galaxy's mass. When you look at a picture of a galaxy, you're seeing less than 15% of what's actually there. Without dark matter, galaxies would never have formed. In the early universe, gas was nearly uniform. Tiny density fluctuations, only 1 part in 100,000, existed. But normal matter interacts with radiation. When gas collapses under gravity, it heats up. Hot gas emits radiation. Radiation creates pressure. That pressure pushes back against gravity. Collapse slows. Sometimes it stops. But dark matter doesn't interact with radiation. It doesn't feel radiation pressure. It doesn't emit light. It doesn't absorb light. It only feels gravity. So in the early universe, dark matter collapsed first. It formed gravitational wells, massive invisible scaffolds. Normal matter fell into those wells, concentrated, compressed, eventually forming stars. Dark matter built the framework. Normal matter filled it in. Galaxies are basically luminous decorations hanging inside invisible gravitational skeletons. And here's the part that should make you uncomfortable. Dark matter outweighs normal matter by about 6 to 1. About 27% of the universe's total mass energy is dark matter. Only 5% is normal matter, the kind that makes up atoms, planets, people. That means everything you've ever touched, every mountain, every ocean, every star you've ever seen, is a minority component of reality. You are made from the rarest form of matter in the cosmos, and the dominant form passes through you silently, right now. Scientists have tried to catch it. Massive underground detectors sit buried deep beneath mountains, shielded from cosmic rays, waiting, hoping a dark matter particle might collide with a normal atom. Just once. So far, nothing conclusive. So far, nothing. Particle accelerators like the CERN smash protons together at extreme energies, looking for missing energy signatures, looking for invisible particles escaping detection. Still no confirmed discovery. We have names for candidates: WIMPs, weakly interacting massive particles; axions, ultralight hypothetical fields; primordial black holes; modified gravity theories. But none are proven. We know dark matter exists because of its gravitational effects. But we don't know what it is. Think about that. We have mapped galaxies billions of light years away. We can detect gravitational waves from black hole collisions. We have imaged the shadow of a black hole. And yet 27% of the universe is made of something we cannot identify. It's like discovering that most of your house is built from invisible beams you cannot see or touch, and you only know they exist because the roof hasn't collapsed. But dark matter, and as strange as it is not the most disturbing part of the story. Dark matter builds structure. It allows galaxies to form. It holds stars in place. It gives the universe shape. There is something else, something even stranger, something that does the opposite, something that is not holding the universe together, but pulling it apart. In 1998, astronomers made a discovery that shattered our understanding of cosmic destiny. The universe isn't just expanding. It's accelerating, which means something is pushing space outward, relentlessly. And that force now dominates everything. Dark matter built the scaffolding. Dark energy is tearing it down. In the next segment, we confront the force that is slowly unmaking the cosmos. For most of the 20th century, astronomers believed they understood the universe's fate. The universe began in a hot, dense state, the Big Bang. It expanded. And because gravity pulls matter together, that expansion should gradually slow down. It was simple logic. Throw a ball upward. Gravity slows it. The universe filled with matter should behave the same way. The only question was, would gravity slow expansion enough to eventually reverse it? Would the universe collapse in a big crunch? Or would it expand forever, but slower and slower, fading gently into darkness? Those were the only options anyone seriously considered. Until 1998, two independent teams of astronomers were studying distant exploding stars called Type 1a supernovae. These are special. A Type 1a supernova happens when a white dwarf star pulls matter from a companion star. When it reaches a precise critical mass, about 1.4 times the mass of the Sun, it detonates in a catastrophic nuclear explosion. And here's why that matters. Because they all explode at nearly the same mass, they all shine with nearly the same intrinsic brightness. That makes them standard candles. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it is. Distance equals brightness drop-off. Precise, reliable. So astronomers used these supernovae to measure how fast the universe was expanding in the distant past. And they expected to find that expansion was slowing. Instead, they found something impossible. The distant supernovae were dimmer than expected, which meant they were farther away than predicted, which meant the universe had expanded more than expected, which meant expansion wasn't slowing down. It was speeding up. The universe's expansion is accelerating. That changes everything. Acceleration means something is pushing space outward. And not galaxies flying through space. Space itself expanding faster over time. Imagine dots on a balloon. As you inflate the balloon, the dots move apart. Now imagine that instead of inflating steadily, the balloon inflates faster and faster. That's our universe. And the cause? We call it dark energy. But that name is not an explanation, it's a confession of ignorance. Dark energy makes up about 68% of the universe's total mass energy content. I said dark matter is about 27%. Normal matter and everything you can see is about 5%. That means 95% of the universe is made of things we do not understand. Dark energy is the dominant component. It controls the universe's large-scale fate. But what is it? The simplest explanation is something Einstein introduced in 1917 and later called his biggest blunder: the cosmological constant. Albert Einstein added a term to his equations of general relativity: a repulsive force built into space itself. At the time, he thought the universe was static. He needed something to counteract gravity's pull. But when Edwin Hubble discovered that galaxies were receding from us, that the universe is expanding, Einstein abandoned the idea. He didn't need it anymore. Or so he thought. Now it appears he may have been right for the wrong reason. In quantum field theory, even empty space isn't truly empty. Fields permeate all of space. And even in their lowest energy state, these fields have non-zero energy, vacuum energy, if space itself contains energy. And that energy density remains constant as space expands. Then, as the universe grows larger, the total amount of vacuum energy increases. More space means more dark energy. More dark energy means stronger acceleration, which creates more space, which creates more dark energy. A feedback loop, acceleration feeding acceleration. But there's a problem. When physicists calculate the expected vacuum energy from quantum field theory, they get a number that is 10 to the 120th power larger than what we observe, 1 followed by 120 zeros. This discrepancy is the worst theoretical prediction in physics. Something is deeply wrong. Either our understanding of quantum fields is incomplete, or some unknown mechanism cancels almost all vacuum energy with incredible precision, leaving only a tiny residue. Enough to accelerate the universe, but not enough to rip it apart immediately. We don't know which. What we do know is this: dark energy began dominating the universe about 5 billion years ago. Before that, matter's gravity slowed expansion, structures formed, galaxies clustered, the cosmic web emerged. But as expansion diluted matter, dark energy remained constant. Eventually, it overtook matter, and acceleration began. But from that moment forward, the universe started becoming emptier at an accelerating rate. Here's what that means for the future. Right now, we can observe galaxies up to about 46.5 billion light-years away. That's the radius of the observable universe. But many of those galaxies are already receding faster than light, not because they're breaking relativity, but because space between us and them is expanding. Light leaving those galaxies today will never reach us. We see them only because we're receiving ancient light emitted billions of years ago. As time passes, more galaxies will cross the cosmic horizon. One by one, they will fade, redshifted into invisibility, until only our local gravitationally bound region remains visible. The Andromeda Galaxy and the Milky Way are moving toward each other. They will merge in about 4 billion years, forming a single massive elliptical galaxy. That structure will remain bound. But everything beyond our local group will eventually disappear from view. Future civilizations, trillions of years from now, will look up at the sky and see only one galaxy. They will have no evidence of cosmic expansion, no evidence of the Big Bang, no cosmic microwave background, no distant galaxies. The universe will appear static and isolated. Cosmology will be impossible. We live in a uniquely privileged window of cosmic history. Yet right now is the only era when the universe is both structured and observable. Too early, and the universe was opaque and chaotic. Too late, and it becomes isolated and silent. We are in the narrow middle, the brief moment when the cosmos can still be understood. And if dark energy remains constant, the universe heads toward heat death. If dark energy grows stronger, there is an even more terrifying possibility: the Big Rip. In this scenario, our dark energy's density increases over time. Acceleration becomes extreme. Eventually, expansion overcomes gravity even inside galaxies. Galaxy clusters dissolve. Galaxies tear apart. Stars drift away from each other. Then planetary systems disintegrate. Then planets are torn from atoms. Eventually, even atomic nuclei cannot hold together. Reality itself is ripped apart. Space stretches faster than the forces binding matter. Everything ends not in fire. And not in ice, but in separation, forever. Most evidence suggests this extreme scenario is unlikely. Dark energy appears constant, which leads to a slower but equally final outcome. Heat death, a universe expanding forever, cooling forever, spreading matter thinner and thinner until nothing meaningful can happen. The universe is not just empty, it is actively emptying itself. The cosmic web is thinning, voids are growing, galaxies are isolating. And over trillions of years, structure dissolves. But this raises a deeper question. If emptiness is increasing, why was there structure at all? Why did galaxies ever form? Why didn't expansion prevent matter from clumping from the very beginning? To answer that, we have to go back further than dark energy, further than galaxies, further than stars, back to the first fraction of a second after the Big Bang. Because the seeds of all structure were quantum fluctuations, and if those fluctuations had been slightly different, we wouldn't be here. In the next segment, we go deeper into time, to the moment the universe decided how empty it would become. Everything you see in the universe, every galaxy, every star, every planet, began as a fluctuation, a tiny imperfection. 1 part in 100,000, that's all it took. As if the early universe had been perfectly smooth, perfectly uniform, nothing would have formed. No galaxies, no stars, no structure, just hydrogen and helium spreading thinner and thinner as space expanded. But it wasn't perfectly smooth, it had wrinkles, and those wrinkles came from something astonishing: quantum noise. To understand this, we have to go back further than galaxies, further than stars. But back to a time when the entire observable universe was smaller than a proton. In the first fraction of a second after the Big Bang, something extraordinary happened. Space expanded faster than light, exponentially. This event is called cosmic inflation. During inflation, the universe doubled in size again and again and again in a period shorter than 10 to the power of minus 32 seconds. That's a decimal point followed by 31 zeros before you reach a 1. At an interval so brief it almost defies language. Before inflation, everything that would become the observable universe fit inside a region smaller than an atomic nucleus. After inflation, that region was stretched to macroscopic size, and then expansion slowed to its normal pace. Inflation solved multiple cosmic puzzles at once. It explains why the universe is so uniform. It explains why space appears flat, but most importantly, it explains why anything exists at all. And at quantum scales, nothing is perfectly stable. Fields fluctuate randomly due to the uncertainty principle. Tiny variations in energy pop in and out of existence constantly. Normally, these fluctuations are microscopic and irrelevant, but during inflation, those quantum fluctuations were stretched to cosmic scales. A fluctuation smaller than a proton became larger than galaxies. Those fluctuations became density variations, regions slightly denser than average. A region slightly less dense than average. When inflation ended, those variations were frozen into the fabric of space. We can still see them today, imprinted on the cosmic microwave background. Cosmic microwave background radiation is the afterglow of the Big Bang, a faint microwave signal filling all of space at about 2.7 Kelvin. It is astonishingly uniform, but not perfectly. It varies by about 1 part in 100,000. Now, those tiny temperature variations correspond to density variations. Hotter regions were slightly denser, cooler regions slightly less dense, and over billions of years, gravity amplified those tiny differences. Denser regions pulled in more matter. More matter meant stronger gravity. Stronger gravity pulled in even more matter. Positive feedback. Eventually, those regions collapsed into galaxies. The less dense regions lost matter to their denser neighbors. They became cosmic voids, emptier and emptier. The universe's large-scale structure, the cosmic web of filaments and voids, emerged from quantum fluctuations stretched by inflation. If those fluctuations had been zero, nothing would exist. If they had been much larger, the universe would have collapsed into black holes almost immediately. Structure requires imbalance, but only a precise amount. Too smooth and nothing forms. Too clumpy, and everything collapses. We live in the narrow band between chaos and uniformity, and now we reach a deeper layer of emptiness. Cosmic voids. When astronomers began mapping galaxies in 3 dimensions in the late 20th century, they expected a roughly even distribution. Instead, they discovered something haunting. Galaxies are arranged in filaments, long strands stretching across hundreds of millions of light years. At the intersections of those filaments are clusters, dense nodes of galaxies, and between them, vast regions containing almost nothing, voids. One of the first discovered was the Boötes Void, a region about 330 million light-years across, containing only about 60 galaxies. A typical region that size would contain thousands. From inside the Boötes Void, the universe would look profoundly empty. The nearest significant galaxy cluster would be over 150 million light-years away in any direction. Now, an observer there might believe the universe contained almost nothing at all. And here's what makes it even more unsettling. Voids are not rare. They dominate the universe's volume. Most of space lies inside cosmic voids. Galaxies occupy thin filaments. The rest is vast, expanding darkness. And those voids are growing, because dark energy accelerates expansion. Underdense regions expand faster than average. Overdense regions expand slower, or even collapse. As the rich get richer, the poor get poorer. Filaments grow denser. Voids grow emptier. The cosmic web is becoming more extreme over time. Now imagine the far future. 10 billion years from now. 100 billion. 1 trillion. Galaxies not gravitationally bound to us will have crossed the cosmic horizon. Gone. Redshifted into invisibility. The cosmic microwave background will stretch to wavelengths longer than galaxies themselves. Undetectable. Now all evidence of this Big Bang erased by expansion. Future civilizations, if any exist, will look up and see only their own galaxy. They will believe they live in a static, isolated universe. They will never know about the cosmic web, never know about expansion, never know about the Big Bang. We exist at a rare moment when the universe is both structured and observable. In the deep past, it was too chaotic. In the deep future, it will be too empty. And now is the narrow window, and isolation will only deepen. Star formation is already declining. Galaxies are using up their gas. Over the next 100 trillion years, the universe will enter the end of the stelliferous era, the age of stars. New stars will stop forming. Existing stars will burn out. White dwarfs will cool. Neutron stars will fade. Black holes will dominate. Eventually, even black holes evaporate through Hawking radiation. It is Stephen Hawking showed that black holes are not eternal. Over unimaginable timescales, 10 to the power of 67 years for stellar black holes, 10 to the power of 100 years for supermassive ones, they radiate away their mass. The final flash releases enormous energy, then nothing, darkness. After that, perhaps proton decay. If protons are unstable over extremely long timescales, then even atoms will dissolve. Matter itself may not survive. The universe approaches maximum entropy. Heat death. A state of total equilibrium. No gradients, no structure, no change, no events. The interesting era of the universe, the era of galaxies and life, is a flicker at the beginning, an infinitesimal fraction of cosmic time. Most of eternity is silence. Most of eternity is empty. And yet, we are not there yet. We live in the bright middle. In the age of structure, in the age when galaxies still shine, and in the age when the cosmic microwave background is still detectable, in the age when expansion can still be measured, in the age when understanding is possible. But why this era? Why now? Why do we find ourselves at the only time in cosmic history when the universe is structured and observable? That question leads to something even more unsettling. The universe might not be finely tuned for life. We might simply exist because only a universe like this allows observers to exist at all. In the final segment, we confront the anthropic principle, fine-tuning, and the possibility that emptiness itself is the reason we are here. The universe is empty, not poetically empty, not metaphorically empty, physically empty. Almost all of space contains almost nothing. Almost all of time will contain almost nothing happening. And yet, here we are. Which raises a dangerous question. Why does anything exist at all? Let's imagine a slightly different universe, one where the initial density fluctuations after inflation were just a little smaller, not zero, just slightly weaker. Gravity would struggle to amplify them, gas would spread too thin, galaxies might never form, no stars, no heavy elements, no planets, just a faint hydrogen fog expanding forever. Now imagine a universe where those fluctuations were slightly larger. Gravity would amplify them too quickly. Matter would collapse violently. Black holes would form everywhere. The universe would become a graveyard of collapsed singularities before stable stars could ignite. Again, no planets, no chemistry, no life. The amplitude of those primordial fluctuations had to be exactly in the narrow band that allows gradual structure formation. And it was. Yet now consider dark matter. If there were less dark matter, galaxies would struggle to form before expansion diluted gas beyond recovery. If there were more, structures might collapse too quickly. Dark matter had to be abundant, but not dominant to the point of instability. And it is. Now consider dark energy. If dark energy had been stronger in the early universe, expansion would have accelerated before gravity had time to assemble galaxies. Its structure formation would have been cut off. If dark energy were weaker, gravity might have eventually reversed expansion. A big crunch, or a radically different cosmic timeline. Instead, dark energy is strong enough to dominate eventually, but weak enough to allow billions of years of galaxy formation first. It waits, then it takes over, just late enough. You can keep going. If the strength of electromagnetism were slightly different, the atoms might not hold together. If the strong nuclear force were slightly weaker, protons and neutrons might not bind into stable nuclei. If it were slightly stronger, fusion inside stars would proceed too rapidly. If gravity were slightly stronger, stars would burn too quickly. If slightly weaker, stars might never ignite. The constants of physics sit inside narrow windows that permit complexity. This is called the fine-tuning problem. And there are only a few ways to interpret it. One explanation is design, that the universe was intentionally configured for life. Another is necessity, that deeper physical laws force these values to be what they are. A third is the multiverse. If there are countless universes with different physical constants, then most of them are sterile, empty forever. But in a small fraction, conditions permit structure, and observers naturally find themselves in one of those rare universes. This idea is tied to something called the anthropic principle. We observe the universe to be compatible with life, because if it weren't, we wouldn't be here to observe it. But the anthropic principle extends beyond physical constants. It applies to time. The universe is about 13.8 billion years old. Stars will continue forming for roughly 100 trillion years. That means we are incredibly early. Less than 1% into the age of stars. The vast majority of stars that will ever exist haven't even formed yet. The vast majority of potential life hasn't emerged yet. And yet, we exist now, in the early middle of the stelliferous era. Why? Because this is the era when the universe is observable. Earlier than this, the universe was too chaotic. Later than this, cosmic expansion isolates everything. The cosmic microwave background fades. Its distant galaxies disappear. Cosmology becomes impossible. Right now is the only era when intelligent life can both exist and measure the universe's origin. We live in the observational sweet spot, not because the universe was designed around us, but because only in this window can observers arise and discover the truth. And what truth have we discovered? That the universe is mostly empty, that dark matter outweighs visible matter, that dark energy dominates everything, that expansion is accelerating, that galaxies are temporary structures, that stars will die, that black holes will evaporate, that entropy will win, that the final state is heat death. The universe doesn't end with drama. It fades, gradually, irreversibly, into maximum entropy, into equilibrium, into silence. From the perspective of eternity, the age of structure is almost nothing. Stars shine for trillions of years, but black holes endure for 10 to the power of 100 years, and beyond that, perhaps infinity. The interesting era of the universe, the era of galaxies and life and consciousness, is an infinitesimal fraction of cosmic time, a flicker, a spark, a brief defiance of equilibrium. Most of existence is empty. Most of time is dark. And yet this flicker happened, on at least one planet orbiting an ordinary star inside an unremarkable spiral galaxy. A Milky Way in a thin filament of matter suspended in cosmic void. On a rocky world in the habitable zone, Earth chemistry became biology. Biology became consciousness. Consciousness became curiosity. And curiosity turned its gaze outward. There is something almost paradoxical about this. A universe trending toward emptiness, produced observers capable of understanding emptiness. Now, in a cosmos governed by entropy, generated temporary islands of order capable of predicting entropy's victory. Matter organized itself into structures that can measure the expansion of space. Atoms assembled into brains that can comprehend cosmic acceleration. We are not central. We are not privileged by location. We are not the purpose of creation. But we are rare, and rarity creates meaning. Yeah, and if galaxies were packed together like grains of sand, if stars filled every direction densely, if structure were everywhere, our existence would not feel extraordinary. But it isn't everywhere. It is sparse, scattered, fragile. The universe is overwhelmingly empty, which makes the rare pockets of complexity profoundly significant. We are not separate from the cosmos. We are a process within it, a temporary configuration of matter and energy. The universe observing itself. And that changes the emotional weight of emptiness. An empty universe without observers is just empty. An empty universe with observers becomes context. The darkness becomes backdrop. The void becomes stage, and consciousness becomes the rare event that gives the stage meaning. Someday, trillions of years from now, galaxies will be gone from view. Stars will fade. Black holes will evaporate. Protons may decay. Heat death will settle in. No gradients, no change, no structure. But right now, the universe has structure. It has galaxies. It has stars. It has life. It has minds capable of tracing cosmic history from inflation to entropy. This is the brief era when the universe is both alive with structure and capable of reflection. And we are inside it. The sky feels full, but it isn't. It only looks full because our brains compress incomprehensible scale into visible points of light. In reality, the universe is an ocean of darkness. Thin strands of matter stretched across unimaginable distances, dark matter scaffolding invisible structures, dark energy stretching them apart, voids expanding, entropy increasing, isolation deepening. The emptiness is real, and it is growing. But so is understanding. And understanding may be the rarest phenomenon in the cosmos. In an ocean of nothing, something noticed, and that might be the most extraordinary thing of all.